So very good evening again to all of you. Welcome to PW Platform Operating System course. Discussion of the topic memory management. And we had seen abstract view of memory where I talked about capacity and addressability at byte level, word level. And we also talked about the interfacing part, how the memory is connected to the processor. And the concept of address bus, data bus, control bus, and subsequently we started with the basic foundations called loading and linking. I talked about two types of loading, static and dynamic, and then we also talked about linking as the process of resolving external references. The external references can come in the form of either functions or global variables. Like for example, in C language, you have a storage class by name 𝐂𝐤𝐧𝐤𝐬, E-X-E-R-N, 𝐂𝐤𝐧𝐤𝐬. So whenever we define a variable 𝐂𝐤𝐧, that means it is actually defined as a global variable in some other file external to this. So resolution of external variables is also done by linker. So that linking can be done, linkage editing can be done either statically or dynamically. Static linking will have the requirement that all the modules, whether required or not required at runtime, you have to link them. Means the size of the executable file will be sum of all the modules of the program, all the libraries, etc. Yesterday I discussed that. On the other hand, with dynamic linking, linking is postponed till runtime. That philosophy in programming, particularly object-oriented paradigms, it is called late binding. Late binding is like dynamic linking. Linking of the external references present in the object module or executable file is done at runtime. How is that done? You will see. But I told a point, if you remember and recollect, that the size, the libraries which are linked dynamically at runtime, are called dynamic link libraries, DLL. The Windows operating system particularly deploys the concept of DLLs, dynamic link libraries, right? So how is dynamic linking done? What is the general procedure? Let us try to have. So today's agenda would be to focus on dynamic linking and also concentrate on address binding. Then we'll have the discussion on memory management techniques. We talk about functions and goals, classification, and then we'll start with the first allocation technique called contiguous allocation. So I will start my discussion today with dynamic linking. See you on board. I take the same or similar program structure which I took in my last class. Say for example, I have function main, calling function f. A function f is present maybe in some other file, you can say. Calling scanf. Scanf is present in the library, compiler library, lib file, right? At runtime, as I mentioned earlier, the compiler, what it does is, because it does not know the address of it, so what happens is, for dynamic linking, right, apart from BSA and blank, every external reference will be associated with a small piece of code which is generally called stub, S-T-U-B, stub. Every unresolved reference in the object file, when I create the object file for this .obj, the .obj will contain a small piece of code associated with external reference by name stub. Stub is a small piece of code associated with every external reference. So here also I will have a stub, BSA dash, followed by a stub. And secondly, I would like to emphasize, I would like to tell you that the size of the executable program, .exe file, will be nothing but the size of main. For example, the size of main, imagine, is 15 KB. The size of function f is 5 KB. Let us say the scanf is 25 KB. So static linking, the total size of the program would have been 45 KB, sum of all. Static linking, the whole size of 𝐂𝐸 would have been 45 KB, sum of all. 25 plus 5 plus 15. But now with dynamic linking, the size of 𝐂𝐸, size of .exe will be the size of main, which is nothing but only 15 KB. So 15 KB of memory is sufficient enough to begin the execution of it. As such, in the memory, I will load the module of size 15 KB. Imagine this is the memory. So I will load the module of 15 KB main function, write .exe file and start executing until the BSA unresolved reference with stub is called. This is a stub. So the moment I involve the external reference at runtime, the moment this happens, this stub get activated. It's a piece of code, it executes. The execution of stub will involve activation of linker, dynamic linker. The linker is given the information about this function. It says that there is a function by name so and so having so and so attributes, etc. Then the job of linker is to see whether that particular function, is it already present in memory or not. Is it already present, like scanf? It is present already in the memory or not. Suppose, for example, the code of scanf is already present in memory. Let us say it is already present at location X. Then the linker will supply address X, and then we transfer the control here, execute the function and return. That is dynamic linking. So linking has been done at runtime. Sometimes what happens is the call function through the linker may not be present in memory. Like scanf may not be present, it may be present on disk. Then in that case, the dynamic linker would call loader. Loader will locate that object file, that module, that library on disk, and then will bring it into main memory, and then the resolution is done and function activation takes place. Generally, dynamic linking implies dynamic loading because of this reason, because the call function or the library may not be present in the memory. So in that case, we have to dynamically load the program, module or the library from disk to memory. This is dynamic linking. Linking postponed till runtime is dynamic linking. What are the relative benefits of dynamic linking? Benefits. So if you write it here, what do you think are the benefits? Can you imagine? Can you imagine what should be the benefits of linking, dynamic linking? Number one, space efficiency. Because those modules only will be linked which are needed at runtime. I unnecessarily don't link those modules which are not needed. Space efficiency. Next, reusability possible, reusability of libraries. Reusability. Meaning, this scanf copy, I need to have only one copy which can be used by different applications. That's not possible in static linking. If I have scanf, if I use static linking, then different C applications need to have their own copy of scanf under static linking. But under dynamic linking, I can have only one copy of scanf present in memory, and that can be reused by different applications. So a lot of space efficiency because of this reusability. Third benefit is basically you can say flexibility. Flexibility of what? Flexibility of updations. If I want to change the library function or library implementation, if I want to change, upgrade, that's very easily possible in dynamic linking but not in static linking. Because in dynamic linking I have to update only the library without touching the applications, but in static linking I have to modify the applications as such. I will have to recompile all the applications. Here recompiling of all applications is not needed because I have only one copy of library. Flexibility. So essentially these are the benefits: space efficiency, reusability, and flexibility of updations or upgradations of the library. These are benefits of dynamic linking. But at the same time, there are drawbacks of dynamic linking also. Can you realize what may be the drawbacks of dynamic linking? The drawbacks, number one is time. The time of linking will be added to execution time now. It becomes slow. Dynamic linking becomes slow like dynamic loading. Program execution time may increase. Subsequently, security threat is more in the case of dynamic linking. Security threat. This is more exposed to danger. It is quite possible that the attackers may corrupt your library, may replace scanf with their own surreptitious secret code. The hackers may replace the original library with their own library, and the applications may get surrendered to the attacker code, and hence security issue. Dynamic linking is less secure than static linking. That's another drawback. Yes, code injection. That's very much possible in dynamic linking. Why? Because the path to the library is not known till runtime. That was a gate question once. Which one is more secure, which one is insecure? The path to the library is not known till runtime. There is always a possibility that the attackers may inject, may perform some surreptitious operation, secret operation. So that is the relative merits and demerits of static and dynamic linking. So next we will start with another fundamental concept before we begin our discussion with memory management techniques, that is called address binding. Actually, binding is a concept of programming. 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 So I would explain what is the meaning of binding. So let me write down the definition of binding first. Association of attributes to entities. Association of attributes to entities is called binding. So in one word you can say binding is nothing but association. In one word you can say binding is nothing but association. Association of attributes, attributes means properties, to elements, to entities, it is called binding. The concept of binding can be applicable to anything. Like for example, I take my case, myself. I am a human being. As a human being, I am an entity in this world and I am associated with several attributes. Like, what are my attributes? First attribute, my name, Khalil Khan. My age, whatever value. My height, whatever value. My weight, whatever value. My place, my address, where I stay. These are called attributes of mine. Attributes, my qualifications. So many attributes. This is an entity by name pen. This has attributes. What are the attributes of this pen? Color, height, weight, etc. Like that, any entity as such will always have attributes. Association of those attributes is called binding. Binding. And the time at which that association takes place, the time at which the association takes place is called binding time. Particularly binding time is important in programming. Binding time. Time at which the association takes place. Like if you ask my name binding, when am I associated with my name? At birth time perhaps, maybe 1 week after birth, maybe 10 days, maybe 15 days. But certainly you don't say that my name was associated at the age of 25 years. That's wrong. That's not correct. Name binding maybe take not more than 10 days, 15 days after the birth. So that is binding time. Correct? Acquiring educational qualifications of 10th class, for example, may happen at the age of 15 years, not more than that perhaps, not less than that. So every binding will have a time at which it gets associated, that is called binding time. Okay. Now when you come to programming paradigms, see on board. If I define a variable like int x, x is equal to 5. Look at this simple point. Look at this. There are several bindings here, several bindings with this. The entity, this is called the entity. This is called the entity. Can you tell me some of the bindings of this entity? Tell me some bindings of this entity. Variable, correct. The entity is variable. What are the bindings of this variable? Come on, tell me. Entity name is variable. First binding is name. Name of this variable is X. Next binding type, integer. Next binding size, 2 bytes, for example. Next binding, tell me what could be that? Address. Very correct. This is what we are interested in. What is this? Next, value binding. Like that, there are others also. Listen here. Name X, type integer, size 2 bytes, address. Like if I go for some implementation, if I say that in the memory, X is stored here. This is a variable X occupying 2 bytes, starting at location 2020 something. This is address binding. The variable X is associated with this address, and I store the value here, 5. Right? Now listen. The time at which these binding takes place are called binding time. For programming, tell me please, from your exposure of programming, tell me, what are the different binding times? What are the different binding times? Tell me. The different times at which the bindings will take place. Come on. What are the different binding times? What are the different times at which this binding takes place? Not assignment time. The first time that it takes place is compile time. Load time next. Last will be runtime. Compile time, load time, and runtime. Alright? Some binding takes place during compile time, some binding takes place during load time, some binding takes place during runtime. Come on, let us understand. Assigning name, type, and size for this variable takes place during compile time. This is called compile time binding. Listen and answer me here, boys and girls. This value is assigned, right? X equal to 5. Let me ask, assigning this value X equal to 5 takes place during dash time. Compile, load, or run? Come on, answer me. One more question. Assigning the value 5 to variable X takes place during dash binding time. It's a simple one mark question. If you are having good versatile programming experience, then what time X is assigned the value 5? This will take place during runtime because this is an instruction. It's an instruction. It will get compiled into instruction like load or store, you can say. Store into variable X, constant 5. I have to execute this. This instruction has to be executed. Runtime. Please understand, that's what I said. Programming exposure is necessary for this. It's an instruction, you have to execute the instruction. And instruction execution happens at runtime. So assigning the value is not initialization. Here it is execution of a statement. On the other hand, we have an interesting programming paradigm here. Let me see how many of you are knowledgeable. Suppose, for example, this is interesting. If I write like int x equal to 5. Int x equal to 5. Listen, in this scenario, in this declaration now. Now this is not an executable part. Variable X, name binding, type binding, size binding, compile time. But now the value binding here, interesting part, value binding here takes place during dash time. Compile, load, or run. Again, one more question. Here we said run time. Here what time? Here what time? This is initialization implicit in the declaration. So what time this happens? Mehnaz Yasmin, Jayendra Pawar. No. Boys and girls, not runtime. This is not runtime Ankush Kautikar. This is not runtime because this is not any executable statement. No executable instruction will be generated for this declaration. This is not during load time, compile time also, because compiler will never allocate memory. To store the value, I need to have memory. I need to have 2 bytes. Compile time, you never allocate memory. So therefore, this is load time. Sudhir is correct. These are all interesting aspects of program elements, programming. This is load time. When I'm loading the program or program module, at that time, I allocate memory and assign the value. It is not during compile time. Because during compilation, memory is never allocated. I hope you understand that point. Am I clear, boys and girls? Okay. So now, if you see the definition of binding as far as operating system is concerned. So from operating system perspective, what is address binding? What is address binding? General meaning of address binding, I told you. Now what is address binding from operating system perspective? Let me write it here. Association of instructions and data units. Instructions and data units. Association of program instructions and data units of the program. To memory locations. Memory locations. Locations having addresses is called address binding. Like what I am trying to emphasize here to you is this point. Let's say this is my memory. As per our notion, memory consists of words. Is memory, physical memory. These are words, starting address 0, 1, 2, 3, X, Y, P, and so on. Suppose, for example, if I have my program as follows, int ABC. I write a statement C is equal to A plus B. Right? Data means this variables. This is my data. And instructions will correspond to this. What are the instructions corresponding to this? Let me write it here. The first instruction is load into some register R1 value of A. Instruction 2, load into some register R2 value of B. Instruction 3, add the contents R1 and R2, assuming result is in R1. Fourth instruction, store into variable C, result R1. These 4 instructions form part of your executable code, and this is my data. So when I want to execute the program, I have to store this in memory location, I have to store this in memory locations. So suppose, for example, if I store variable A here, if I store variable B here, if I store C here, so this is binding, address binding. And likewise, if I store instruction I1 here, I2 here, I3 here, I4. So these instructions are bounded to these addresses. That is called address binding. These instructions, these data units are bounded to these addresses, address binding. So this address binding again can be carried out during compile time, I'm writing in short, or load time or run time. This binding of instructions and data to memory locations with addresses can be carried out during compile time, load time or run time. If the compiler does the address binding, compiler decide, here people get confused. Compiler only decide where this instruction, where this data unit should get stored in memory, where. It only decide that. It will not load it, it will not store it, only decide. That is called compile time. If you don't want compiler to be overburdened with address binding, then the next level where you can do address binding is load time. Loader will do it. Compiler will not generate addresses. Compiler will only say that I am generating this code. Loader, you load wherever you want in memory. Loader will do. Loader will do address binding and store the instructions and data units in the memory. Load time address binding. Boys and girls, remember, both compile time and load time address binding, both of them is static. Static means once binding has been done, you cannot change it. Like my name binding is static. My name cannot change. Static. My color, my height, static. Now it is static. Whereas my age is dynamic. Keeps on changing. Right? So that is dynamic. Likewise, the type of the variable is static. The size of the variable is static. Right? And the values may be dynamic. Values will be dynamic. The values which I assign, because it changes during runtime. Address binding can also be static or dynamic. So any binding can be either static or dynamic. So runtime binding generally is dynamic. Means the binding that takes place during runtime, execution time, that is dynamic. So in dynamic binding, what happens is addresses which you have assigned to the variables can change from time to time. Initially I loaded the program here, later I swapped the program out, again swapping into different area, bindings change. So if there is a change in binding, dynamic. If there is no possibility of binding getting changed, that is static. So any binding can be either static or dynamic. So compile time and load time is static. Once compiler has done the binding, loader has done the binding, you cannot change the addresses static. At runtime, if you are able to change the addresses of instructions and data units, runtime binding, dynamic binding. The same scenario can be shown diagrammatically in this case. I would appreciate if you are able to visualize this diagram. That is not the meaning of runtime binding. Let me explain by taking a suitable example. Let me explain by taking a suitable example the philosophy of dynamic binding. Listen, this is memory and this is the disk. Follow me carefully. This is memory. Memory, I mean main memory. This is main memory. And this is disk. Let us say on disk I have some program. Program consists of instructions and data. Follow me carefully, Sudhir. Now suppose we are following runtime address binding. So what happens? Loader will load the program instructions and data starting from location 1000, let us say. So starting from location 1000, I have variable A, variable B, variable C, something like this. And then other instructions are there, starting location 1000. I executed some instructions of the program halfway through. Halfway through I executed instructions of the program. Then after that, the operating system for some reason decided to swap out this program. Follow me, swap out, suspend, swap out, suspend or swap out. For some reason the operating system decided to swap out the program onto disk. So it will be there on disk for some time. Now after some time, if the operating system decide to swap in the program back, follow me carefully, when I decide to swap in the program back into memory, then with compile time and load time address binding, if my program is following compile time or load time address binding, condition is that the program should get into the same area of memory from where it got swapped out. From where it got swapped out. Okay? From where it got swapped out. Same area it should come. That's why it is called static. Addresses are static. With dynamic address binding, it is possible that halfway through I swap out. Then when I swap the program back into memory, it is not necessary it should get into the same area. Maybe I can load the program from location 2500 and continue my program. I will not restart, continue my program from the execution from where it got swapped out earlier. Maybe I have completed 10 instructions swap out. I swap into different area of memory and altogether start the execution from 11th instruction without restart. This is runtime address. That means during runtime, the addresses of the variables got changed. Addresses of the instructions got changed. I hope you are understanding. Let me explain the diagram. I have written some source program like .c. Compiler or assembler generate the object code, this is compile time. If address binding is done during this time, this is called compile time. Object module is generated. All object modules are given to linkage editor. Linkage editor is nothing but linker. Other object modules, scanf, printf, whatever are given. Then loadable module, this is your exe, which is ready to get loaded in memory. So that's why this time is called load time. So loading happens after linking. So first linking, then loading. The loader will take the loadable module and other system libraries which are needed. Loader knows it. Loader will be given information that these modules are needed. So therefore, I have to load in memory. So information will be given. The loader will load them. So now we say in memory. Binary means executable memory image of the program. Now it is runtime. So those modules which are linked at runtime, they are dynamically loaded system library, DLLs. That is dynamic linking. This is dynamic linking. Linking is happening during runtime. So dynamic linking. So if binding takes place here, runtime. If binding takes place here, load time. If binding takes place here, compile time. Very simple diagram. That is very clearly showing what happened during compilation time, what happened during linking time, what happened during loading time, and you should not have any confusion what exactly is linking, loading and execution. That is showing a very clear picture diagram taken from Galvin textbook. To the next topic of discussion will be memory management techniques. Techniques for managing memory. This is nothing but essentially the design of memory manager. So before we see various techniques, it is important that we should discuss functions and goals of memory manager. Functions and goals. The very first function of memory manager is allocation. Allocate the memory. Next, protection. Protection means making sure that one process should not interfere or trespass into other process areas. That is protection. Should not interfere with other areas. Like if you want me to show pictorially, this is a memory. And in this memory, let's say this is program P1, this program P2, process P2, process P3, process P4. So this is called process P1 address space, this P2 address space, P3 address space, P4 address space. So process should not interfere into other address space, others address space. This is called protection. Third function is free space management. Free space management. And fourth is deallocation. These are the general functions carried out by any memory manager implementing some memory management techniques. Allocation, protection, free space management and deallocation. Now to carry out these functions, I should set aside certain goals. What should be the important major goal of memory manager? The important goal is effective or efficient or effective utilization of memory. Memory should not be wasted. Wastage should be kept to the bare minimum. Generally, the term which is used to denote the wastage of memory, what is that? It is called fragmentation. Fragmentation should be less. I'm sure you might have studied fragmentation is of two types, internal and external. We will define what is internal and external fragmentation at appropriate time. We'll define it. So that is one objective goal. Next important goal of memory manager is the ability of memory manager to manage execution of a larger program in small memory areas. Manage the execution of a larger program in small memory area is one of the important goal of memory manager. One of the important goal of memory manager. Diagrammatically, I can make you understand this philosophy of this. Suppose, for example, if this is a disk and this is a memory. The disk is the memory. Memory always will be divided into two parts: operating system, other area is user area, where I load some programs. Say already I have program P1 and P2, and imagine this is a free area of memory right now, free area. Let's say the size of this free area is 80 KB, 80 kilobytes. And on disk I have some program P whose size is, for example, 200K, 200 kilobytes. I wish to execute a program of size 200 kilobytes, but operating system say available memory is only 80K, free. Logically I need 200K, but available is only 80K. The question is, can we means operating system, the memory manager of the operating system, can it manage the execution of 200 KB program in 80 KB? If so, we are supporting this goal. So managing does not mean that we are going to reduce the size of the program from 200 to 80K. No, we are not going to reduce. We are not going to apply techniques like WinRAR or WinZip, where we are reducing the size of the file to 80 KB and execute. No. We are going to manage the execution. How? We have to see that later. How do we manage it? We have techniques for that. Does anybody know some techniques that could do this, that could accomplish this goal? How can we do it? What are the techniques for achieving this? Managing the execution of a larger program in small memory area, what are the techniques for it? Anybody? One of the important prominent techniques which does this, it is called virtual memory. Virtual memory. Through paging concept, demand paging. Virtual memory. There is another technique called overlays that support this goal. Overlays. So these are the two techniques that support the goals of managing the execution of a larger program in small memory area. Now you may be wondering here, see, when I say the goal is to optimize memory and has less wastage, everybody understand what is the benefit of having less wastage. But it is quite essential to know what is the benefit of managing the execution of a larger program in small memory area. Come on, tell me, anybody? What are we going to gain ultimately by managing the execution of a larger program in small memory area? What is the advantage of this goal? Yes, that will increase the degree of multi-programming. I can utilize small chunks of memory and therefore I can load more programs. I can load more programs. If I load more programs, degree of multi-programming will get increased. If degree of multi-programming increases, I can keep my processor busy most often. Throughput will increase. So it will have an impact on throughput. So that's the analysis. Am I clear? So these are the functions and goals of memory manager. Okay. So now to carry out this functionality, yes, it will increase efficiency. To carry out this functionality in achieving these goals, we have techniques of memory management techniques to achieve this functionality and goals, memory management techniques, classification, taxonomy. The memory management techniques are classified into two types. One is called contiguous and the other is non-contiguous. Non-contiguous. I will write contiguous in short as CG. Non-contiguous I will write in short NCG. In my own terms, I would say contiguous is like centralized allocation. Centralized. This is like decentralized or distributed approach. Distributed. In what sense? Let me explain. Suppose for example, if this is memory, centralized or contiguous allocation means the whole program will be at one place centrally, the whole program P. Program of 100 KB will be at one place contiguously, centralized. Whereas in decentralized approach, it is quite possible that this program may be divided into parts, maybe multiple parts. One part of the program I store here P1, another part of the program P2 stored here, another part of the program P3 here, distributed approach. Same program got divided into three parts, part 1, part 2, part 3, distributed, non-contiguous. It is not necessary that the whole program should be at one place centrally. Program may be divided into parts, units, blocks, and distributed in memory at different places, non-contiguous. Both the approaches have limits and demerits, merits and demerits. The techniques, different techniques that comes under contiguous allocation are partitions, or first overlays, second partitions, fixed and variable partitions. These are two important techniques. Of course, both of them are primitive approach. Modern day techniques use non-contiguous. And the techniques that we use here is paging, segmented paging, or segmentation first, and then segmented paging. And then last, virtual memory as a concept also comes under non-contiguous allocation. So this is our philosophy. When I say paging, we are going to learn different forms or types of paging. Paging with TLB, multi-level paging, hash paging, inverted paging, and so on. All will be covered there. Hope the classification is clear. So before I start my discussion, before I take up my discussion to contiguous allocation, I would like to talk about the protection aspect, how generally protection is done. This is a simple diagram to show the protection concept. How process will ascertain whether the address that is generated is within its address domain or within its area of memory or not. So for that I will have registers like base. Base is the starting address. Limit is the size. Limit means size of the program. Like what I am saying, for example, if some program is stored here, the base value is the starting address, 2000. Suppose if I say the total size of this is 500 words, 500 bytes, so limit is 500. So naturally, any address which is generated by the running program on CPU, any address, it has to be lying between 2000 and 2500, is it not? 2000 and 2500. So that's what we check. Is address greater than or equal to base? Yes. If it is no, then it is a trap error to operating system indicating that this is an addressing error if it is less than base. Otherwise, if it is greater than or equal to base, then we add base plus limit 2000 plus 500 and check is it within less than 2500 or not. Yes. If it is greater than 2500, no, again an error. This is a simple hardware support needed for ensuring protection. Simple hardware support for ensuring protection in most of the contiguous allocation techniques. Okay, that's very simple one. Now we will take up the discussion first with the first technique under contiguous, and that's a very primitive one, and that is called overlays. So let's discuss this. As I mentioned earlier, overlaying techniques support the goal of managing the execution of larger program in small memory area. Overlays support the goal of managing the execution of larger program in small memory area. How does it achieve it? How it achieves it? We'll understand the philosophy of overlays by using a concept of two-pass assembler. What is an assembler? Assembler is a translator that translates assembly language program to machine language program. Assembler is a program like compiler, translator that converts assembly language program to machine language program. Generally, these translators, compilers, assemblers, they run in passes. Pass 1, pass 2. As you are aware, compilation passes are lexical analysis, syntax analysis, semantic analysis, and so on. So likewise, assembler can also work in passes, pass 1, pass 2, and so on. So I am taking the case of 2-pass assembler. Follow me, it's very simple and interesting. Say for example, the size of pass 1 program, pass 1, the one who does pass 1 assembly is 70 KB. Let's say. The size of pass 2 program is 80 KB. Let us assume. During both the passes, we may use a data structure called symbol table. Let's say that is 30 KB. Some common routines may be required during both the passes, common routines, that is around 20 KB. And the overlay loader, overlay driver we say, overlay loader is around 10 KB. So if you sum up, the total size becomes, let's say 150, this is 50, 200, 210, total size of memory. Which means that logically under ideal conditions, if I want to assemble my program with this 2-pass assembler, pass 1, pass 2, I need 210 KB of memory. I need 210 KB of memory. But for example, imagine I don't have 210 KB of memory free available. What is available to me? What is available to me is 150 KB. Available free space is 150. Only 150 KB memory free available, but the program needs 210 KB. So now we are going to learn, we are going to study, can we manage the execution of 210 KB program in 150 KB of space? If so, how? If so, how? Using overlay, the traditional meaning or the literal meaning of overlay is replace. If you look at the word overlay, means it is replace. Replace, overlay. So we have basic understanding here. Look here, boys and girls, we have basic understanding that during pass 1, I don't require the code of pass 2, and during pass 2 I don't require the code of pass 1. That means pass 1 and pass 2, both of them are mutually exclusive. Mutually exclusive. During lexical analysis, I don't require the code of syntax analysis. And during syntax analysis, I don't require the code of lexical analysis. Same way. When I'm doing pass 1 assembly, I don't require the program of pass 2, and vice versa. When I do pass 2, I don't need pass 1. So that I can exploit as a property here and perform the execution as follows. So follow here, boys and girls. So what I will do now with overlay, how do I do it? I will load first all those modules which are necessary during both the passes. During both the passes, I need symbol table, so I will load symbol table first in memory. During both the passes, I need common routines. I load them, common routines. Overlay driver always has to be there in memory. Loader or driver both are same. These 30K, these 30K, these 20K, these 10K. The remaining area 150 minus 50, 150 minus 60, 90K. 90 KB chunk of memory is free. So I can say that first I will load pass 1 here, pass 1 program, and complete pass 1. Right? This pass 1 is 90K is sufficient enough to load either pass 1 or pass 2. Once pass 1 assembly is done, then the overlay driver will overlay the code in the same area with pass 2 and complete pass 2. When the modules of the program are independent, mutually exclusive, overlaying is always possible, and then you can accomplish the execution of larger program in small memory area. This is the ideology of overlays. Come on, tell me, Boliye, is it clear? Is the concept clear of overlays? Overlaying is possible only when the modules of the program is divided into modules and the modules are mutually exclusive, independent. Then I can overlay and do it. That's a simple concept. But as I said, the limitation is that this is possible only, as I have been telling you, when the modules are independent. But for example, if the modules are dependent, then we are hopeless. We cannot do overlay. So that's the limitation of overlay. Why compiler? Pass 1 and pass 2 is done during runtime of it. or during compilation time? Yes, naturally. We should be able to, the operating system should be able to do it, because this is a part of operating system. Now, memory management is part of operating system. So, operating system is going to do this. Next point is, there was a gate question based on overlays in one of the exam. I will project the question. It's a similar data. You try to answer it. The question was asked in the form of something called overlay tree of a program. Overlay tree of a program was given. Let me draw the overlay tree. The tree was shown like this. We'll take this much only. I'll put the sizes here: 10 KB, 4 KB, 6 KB, 8 KB, 4 KB. Let us name the modules. Is module A, module B, C, D, E, F, G, H, I, J. Total program size is nothing but sum of all the modules. So 10 plus 4, 14, 20, 28, 32, 38, 43, 47, 53, 55, 63. Total program size is 63 KB, sum of all the modules. Question is, listen to me, boys and girls. Question is, what should be the question? Interesting way of asking the question. What should be the question? Values are different. I put my values. Tell me, what should be the question for this? Yes, that's right. Question is, what is the minimum memory required to execute this program? Minimum memory required to execute this program with overlays, under overlays. Come on, I want you to work out and tell me the answer. Work out and tell me the answer. As a concept, if you want me to write the formula here, it is nothing but minimum of path lengths from root to leaf. All path lengths from root to leaf. These modules are independent: B, C, D, E, F, G, H, I, J, K. This is dependent. So to execute this line, I need 10 plus 4 plus 4, that is 18K. To execute this 6 plus 4, 10, 10 plus 20, 20K. 5 plus 4, 9, 19K. Like that, I have to calculate all and take the maximum. Sorry, here I have written minimum, but maximum. Maximum of path length from root to leaf. So what is that answer? ADK. That's right. 26K. So the answer for this is 26 KB. So if I have 26 kilobytes of memory, I can execute 63 KB program otherwise. That's the advantage of overlaying. But as I said, this is possible only when the program can be broken down into independent modules or mutually exclusive modules. Okay. So that is about overlays. Next, we'll begin our discussion with the second important memory management technique, namely partitions. It's a contiguous allocation. There are two partitioning techniques. One is called fixed partitions and the other is called variable partitions. We'll first take up fixed partitions and then we'll take up variable partitions. Fixed partitions is also called MFT, which stands for multi-programming with fixed tasks. Task or job or program or process, both are same. Fixed partitions. Multi-programming with fixed number of tasks or fixed tasks. So I will start with the basic architecture here, so kindly pay attention. This is memory. I have been repeatedly telling you that memory is generally divided into two parts. One area is called for operating system, and that area is called system area or S area. And the other area of memory is called U area or user area. It is this user area where we load the programs, user programs, multiple user programs. So managing memory means managing user area. So I am taking an enlarged view of this user area, here. Okay. I have enlarged this. So this user area, whatever be the size, I don't take the size, whatever be the size. So when I say fixed partitions, so this user area will be divided into fixed number of partitions. This user area will be divided into fixed number of partitions like this. This is one partition. This is another partition. This is another partition. This is still another partition, and so on. The philosophy is that, the philosophy or the ideology is that, rule you can say, one partition, one process. These are the rule. One partition, one process. That means in one partition we can have only one process. I cannot have two processes in one partition. I cannot have one process occupying in two partitions. Rule is 1:1. One partition can hold only one process. Partitions, because they are holding programs or processes, so naturally partitions may be of different sizes. These partitions may be of different sizes. Like what I am saying, for example, this may be some 80 KB. This may be 120 KB. This may be, let us say, 250 KB. And this may be some 30 KB. This is 100 KB. And this is 300 KB. Something like this. So when I say this is of size under 80 KB, I can load a program of size up to 80 KB here. Not more than that. Less than that, yes, but not more than that. And as far as protection is concerned, I have already told you, base and limit registers, the same hardware will be used for ensuring protection, which I have explained to you here. Protection. And per partition, we are going to maintain a bit flag, which is going to indicate whether partition is free or in use. Whether partition is free or in use. So free space management is done, protection is done. But what is predominantly important to understand here is allocation. Allocation. Meaning, suppose if I get a new process of some size, let us say the size is 50 KB. Size of the program is 50 KB. It can get placed, so we have to decide in which partition are we going to place it. In which partition? There may be many eligible partitions where we can load this program. Many eligible partitions where I can load this program. Maybe I can load here, I can load here or here or here or here. 30 KB I cannot load here or here. So among all the free partitions, which partition are we going to load this program into memory? That is decided by allocation policies called partition allocation policies. Decided by partition allocation policies. We have some standard partition allocation policies. I am sure you might have studied at your undergraduate level. Do you remember what are the various partition allocation policies? At least some of them. 4 allocation policies. We have 4 standard allocation policies. First is called first fit. First fit. We say that first free big enough is first fit. First free big enough partition is first fit. That means when I want to place this process, start searching from the first partition which is big enough and free to place it. Like if all are free, I will place 50 kb in 80 kb. How? Dividing this one, I load 50 kb here and the remaining 30 kb free space will go waste. If I place 50 kb in 80 kb, I will place it wherever I like, however I like. Remaining 80 minus 50, 30 k will go waste, and that wastage is known as dash. 1 mark question. The amount of memory that is going waste within the partition after the placement of the process is known as dash. What do you call that wastage of memory? Internal fragmentation. That's right. That is called internal fragmentation. Internal because it is within the partition. Internal. So I may have internal fragmentation. Okay. We'll talk about next. Best fit. What is best fit? As the name say, best with regard to least internal fragmentation. So therefore we say smallest free big enough. I would say that out of all partitions, whichever is smallest and free and big enough, you place it. Best fit. Like here, for 50k, smallest is 80k, I'll place it there. Best fit. Okay, smallest free big enough. Next is worst fit. Worst fit. Largest free big enough. Out of all the largest. Largest. That is worst. Like 50k, if all are free, it will go into 300k. If 300k is in use, it will go to 250k. Largest free is worst fit. Last is next fit. Next fit works like first fit. Works like first fit exactly, except that the search for free partition, search for free big enough partition, search for free big enough partition commences from partition where last allocation was made. Look at that. After the last search, yes. I will take a situation for explaining this. Imagine, for example, in our scenario, this partition is in use, this is in use, this is in use. And this was my last allocation, LA, last allocation. Last allocation was made here. And I want to allocate 50 kb. Listen to me, boys and girls. 50 kb. Using first fit, I will place 50 kb in 80 kb. First fit. Using next fit, where will 50 kb go? Come on, answer me. Using next fit. Using next fit, where will 50 kb go? Using next fit. Then now I will ask you, what is the logic behind searching from last allocation? Now why not from beginning? What is the logic, advantage of searching from last allocation? So invariably I am asking you, what is the advantage of next fit over first fit? What may be the advantage of next fit over first fit? Come on. There should be some advantage of the searching from last allocation rather than from beginning. So what may be the advantage of next fit over first fit? Come on. The advantage is next fit may work faster. How? Because if I believe that, listen now, you can see the scenario. If I believe that this is also in use, then using first fit, 50 kb will go into 100 kb using first fit. But after making so many comparisons, so much search, I have come here. If I search from last allocation, the probability that the next partition is free is big enough, is good. So therefore, it may involve less searching time. Yes. The place where last allocation was made means the next partition may be free. So I can allocate faster. The next fit may work faster to first fit. So these are the various allocation policies. Boys and girls, I would like to tell you that fixed partitioning approach is like a static approach, because once I create the partitions, I cannot remove it until I shut down my system. It is static. Once I create 5 partitions, 6 partitions, whatever, it will remain static. I cannot change the number of partitions. I cannot change the size of partitions. So in regard to this, let us see the performance of fixed partitions. Performance. First point, as part of performance, can it suffer from internal fragmentation? Just now we visualized. Can it suffer from internal fragmentation? Yes, it suffers. It may suffer. Second, can it have external fragmentation? Still, I have not yet defined what is external fragmentation, but however, I can give an idea, simple idea. Actual definition will come shortly. External means, listen, outside the partition. See, in between the two partitions, there is no scope of having any free space. There is no free space. External means outside. Since there is no scope for having any free space between the partitions, no scope, so therefore this will never have external fragmentation. Degree of multiprogramming. Degree of multiprogramming is limited. Limited to what? Limited to number of partitions. If I create 6 partitions, I cannot have more than 6 programs at a time. Next. Maximum process size runnable. Maximum process size runnable is also limited. Limited to what? Limited to maximum partition size. If I am creating a partition of 300 KB, I cannot run a program of size more than 300 KB. These are limitations. Then which allocation policy is superior or better? Which one will perform better? Allocation policy. Best fit. Best fit is best. Best fit is superior because of less internal fragmentation. Come on, tell me, is it okay everything? Is everything okay? Performance? So we have internal fragmentation, we have limitation for multiprogramming, we have limitation for maximum process size. So these are the limitations of fixed partition approach. Am I clear? Or any questions or any doubts? Okay, very good. So to overcome these limitations, one can think of going in for variable partitions. Second. Variable partitions. This is also called MVT. Multiprogramming with variable tasks. Earlier FT, fixed tasks, variable tasks. And this is rather, I would say, dynamic partitioning. I would say dynamic partitioning. Partitioning is done dynamically, not runtime, not fixed load time. So I will take a scenario and explain how is MVT done. Let's say this is our memory. As usual, a portion of it for user operating system area, and this is the user area. Again, I enlarge the user area for partitioning. This is user area. User area. There is no fixed partitioning here. The whole user area is one free chunk, one free hole, HOLE, hole. Now suppose, listen, in the disk queue, input queue or job queue, this is a job queue or input queue on disk. There are some programs available to get loaded in memory, P1, P2, P3, P4, P5, like this at time T. This is of size, let us say 80K. These of size 100K, these of size 25K, these of size 120K, these of size 200K. Programs of different sizes. They want to get into memory. So the operating system loader will create partition dynamically at runtime. It will take P1, size 80K, so it will create a new partition, one partition of size 80K, put P1. Next 100K, it will create another partition of size 100K, P2. So right now, boys and girls, there are two partitions, one free hole, like this. Then it will create another partition exactly of size 25K and put P3. Then P4 120K and put here P4. And then P5, 200K, P5. Remaining, let us say 400K is free. So right now, initially I was having 0 partitions and 1 free hole. Now I have 5 partitions and 1 free hole. Dynamic. Then after that, listen to me. There may be other programs right now not available, not allocatable. I don't want to allocate, we'll see later. Now see, this is the CPU. So what happens now? Now, processes get scheduled and they run till completion. Listen to me. After some time, let us say T dash, some processes get completed. Maybe I imagine I completed, listen to me, I completed point number 1. Imagine first I complete P5 for example. For example, if I complete P5, remember, if I complete P5, then what happens? This becomes free, this is free. This is free, this is free. 2 adjacent free holes, this is a free hole now, this is a free hole. 2 adjacent free holes will be automatically merged to one free hole like this. 400 plus 200, so now this will become 600. This is called coalescing. 2 adjacent free holes will be automatically merged into one free hole automatically. That process is called coalescing. So I am taking earlier case only. Earlier case. This is P5, 200K, and this is 400K. Free hole. Okay. Now imagine after some time I completed P3, then I completed P1. Let us imagine. This is a scenario now. So I have got one free hole here of size 80 KB, another free hole of size 25 KB, and here I have 400K, 3 free holes. Sorry. This P2, 25, and P4. So 3 free holes. So at this point of time T dash, I get a new process of size 23 KB. Of size 23 KB. The question is, where should I place? To decide that, where should I place, which free hole am I going to place? I use the same first fit, best fit, worst fit, next fit. But how do I place that is different. If I using first fit, I will place it in 80 KB, right? Creating one partition of size 23K and remaining 57K will be a new free hole. So 80K will get divided into 2 parts. One of size 23 KB partition where I place the process, and then the remaining 57K will be a new free hole. It will be a new free hole. Here, first fit. Best fit I will place in smallest. 2K will be new free hole here, best fit. Worst fit here 400K. Next fit may be again 400K. So therefore, the only point that you need to understand is, if the size of free hole is greater than the size of the incoming process request, then I divide that into 2 parts. One will be partition size, another will be a new free hole. Size of the partition will be equal to size of program, size of process. Am I clear? This is variable partitions. That's why it is dynamic in partitioning. Number of partitions at any time can keep on varying. So based on this, we will make a performance of this again. We'll discuss the performance of this. Same issues. Issues are same. Number 1, you have to tell me, can there be a possibility of internal fragmentation here? Tell me, yes or no? Yes, new freehold has to be used for new process, obviously, Ankush. Why are we saying freehold then? New processes can get placed in freeholds. Can there be a possibility of internal fragmentation here? Yes or no? Jayendra Pawar is saying yes. Is it possible? Jayendra Pawar is saying yes. Is it possible? No, it is impossible. There is no scope, there is no possibility of having internal fragmentation because I am creating a new partition exactly equal to size of program. So where is the question of internal fragmentation? There is never a possibility of internal fragmentation. Like 23 KB, if I place in 80 KB, this 80 KB will get divided into two parts. Listen, this 80 KB will get divided into two parts. This 80 KB. One of size 23 KB and another will be 57 KB. So this 57 KB is a free hole. This is not fragmentation. This is a free hole. I can place new process here in this free hole. So no internal fragmentation. Can there be a possibility of external fragmentation here? Come on. Can there be a possibility of external fragmentation here? Yes, there is a possibility. What is external fragmentation? Let us analyze by taking another example, simple example. What is external fragmentation? I will explain through example. Please follow. Imagine a new memory system where this is some process P1, another free hole, process P2, another free hole, and P3. Three processes are there, whatever be the size, and the size of this free hole is 50 KB, let us say, and the size of this is 80 KB. Total free memory, total free space is how much? Total free memory, total free space is 80 plus 50, 80 plus 50, 130K. Listen. Now suppose, if I get a new process of size 90K. I get a new process of size 90K. Listen. Is it possible to place this new process 90 KB here? No, we cannot. Even though we have sufficient 130 KB space memory. It is outside the partitions, One here, but we cannot place 90 KB. So don't you agree that 130 KB of memory space is going waste or not? Even though I have sufficient space, it is going waste. So this wastage which is happening outside the partitions, these are partition, outside the partitions, it is called external fragmentation. Yes, if no process can fit, even though we have sufficient memory. If the total size of memory would have been 90 KB, would have been less than 90 KB, then no external fragmentation. If this is less than 90 KB, total free space, then no external fragmentation. Because even if it is there contiguously, I cannot break up this process. It is contiguous allocation. I cannot take 50 KB here and the remaining 40 KB here. I cannot do it because it is contiguous. So therefore, this scheme suffers from external fragmentation. Degree of multi-programming earlier was limited. But now I say it is flexible. Maximum process size runnable earlier was limited. Now it is flexible. But more interestingly, we have to see which allocation policy earlier was better. Earlier best fit was better. But now tell me which allocation policy is superior from this example. Which allocation policy should be better? Like take this 23 KB, if I want to place using best fit, it will get placed in 25K, leaving a new small free hole of size just 2K. 2 KB. And if I say that, listen to me. If I say that 2 KB is not sufficient enough to accommodate a new process, 2 KB is too small to accommodate a new process. So in that case, it will go waste always as external fragmentation. It will always go waste as external fragmentation. So what I am saying, best fit allocation policy will result in creating small free holes in variable partitions. It will create small free holes which may always go waste in the form of external fragmentation. So if you don't want to create small free holes, then which allocation policy you think is superior or better here? Worse fit. Worse fit will create larger free holes. Worse fit. Worse fit will create large free holes that can accommodate new processes. So therefore, I say worse fit is superior. Worse fit will create large free hole. Look at this. If I place 23K in 400K, what is the size of the new free hole? It will be 377 kb. 377 kb will be a new free hole that will improve the chance of accommodating a new process. 2 kb cannot accommodate a new process. 373 can well accommodate a new process. So that's why worse fit is better. So what we are saying is how to overcome the problem of external fragmentation. So the only problem that is remaining is external fragmentation. What are the solutions for external fragmentation? Any idea? There are two solutions. There are two solutions for solving the problem of external fragmentation. What is it? Defragmentation. What is the name given to defragmentation? The name given to defragmentation process is called compaction. It is called compaction. Compacting memory, defragmenting memory. So what happens here? Bring all free spaces together, correct? When I compact this memory, boys and girls, 50 and 80, right? I will write inside and do compaction here. Look here. This 50 kb and this 80 kb. When I do compaction for this memory area, the memory area will look like this. This is my memory area now. After compaction, what happens? All processes come at one end, P1. P1 is already here. So I bring P2 immediately after, relocate P2 immediately after P2, P1, P2. Then the remaining area will become one free chunk, and P3 is also there. P3 is also there. So P3, P1, P2 are relocated at one end of memory, creating one free chunk of memory at one end, that is 130K. This is 130K. So I have relocated the program from this area to this area. This is called relocation or compaction. So compaction will create one free hole at one end, and then you can place the process. Advantage of compaction is, okay, it can be carried out easily, but the drawback, one of the drawback or limitation of compaction is it is a time consuming operation. It consumes time. It takes time to move the program from one end of the area of memory to another area. Secondly, can anybody tell me one more question? Answer the question. Compaction is possible only with dash address binding. Compaction of programs, compaction of memory is possible only with dash address binding. 1 mark. Very correct. Runtime. Because during runtime you are moving the program. So therefore, supported by only runtime address binding schemes. Program that support runtime address binding only can go for compaction. Program that support compile time and load time, compaction is not possible. So in view of this, the other solution for external fragmentation problem is called non-contiguous allocation. Non-contiguous allocation. The other solution for overcoming the problem of external fragmentation is go for non-contiguous allocation. Meaning, if I have some free memory here, why should I have the restriction that the whole program should be at one place? Divide the program into modules and place one part of the program here, another part of the program here. That is non-contiguous. So my dear students, what I am trying to say, one of the design goals, one of the objectives of having non-contiguous allocation is to prevent the problem of or overcome the problem of external fragmentation. And the particular technique which is used for this is paging. The particular technique primarily used for solving this problem is paging, external fragmentation. So that we shall take up perhaps in the next class, but here before we close we will take up some problems, some questions of partition. But before that, just let me know, is everything clear of fixed partitions and variable partitions? Everything is clear? Very correct option is C, because 4K 2 power 12 is 4K. Size of the data bus is size of the word 16 bits. So 12 address and 16 bit. That's very correct. Simple question. Now work out this. This is a gate question, PYQ. Please work out this. 1 mark question. What partitions are not allocated or remains unallocated? Very simple 1 mark question. Very simple direct question. I don't have to really work out, but even though I am doing it, 357 will move into where? 400. And then I have 210K. 210 will move into where? 250K using best fit. 210. 468 will go where? 468. 468 will naturally go into 500. And then finally 49. Where will it go? 49 will have to go into 250. Sorry, 250 is done. So where will it go? Come on, tell me. 200K. So what is remaining? You can see that 400 is over, 250 is over, 200 is over, 500 is over. So remaining is 300K and 600K. That's it. Next question. Using first fit, 300K will naturally go into 350K, leaving a new free hole of size 50K. 25 using first fit will get accommodated in 150, leaving a new free hole of size 125K. 125 and 125, 50 and 50. First fit, it is possible. Best fit. 300 will go into 350, free hole 25, 50K. 25 will go into 50K. 125 here, 25 here. So 25, 25, 2 free holes, 50K cannot get accommodated. First fit but not best fit. The correct answer is B. Got it? So this is way questions, simple questions can be asked. Fixed partitions and variable partitions. So we'll close for the class. If you have any questions, you can ask in a minute. So do watch the video, practice the questions and come to the next class. And next class, I'm going to begin my discussion with non-contiguous allocation, where I'll start my discussion with simple paging. That is very, 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 very important. That become foundation for all the remaining topics of memory management. You can follow 𝐂𝐤𝐴𝐿𝐵𝐿 Sudhir. 𝐂𝐿𝐵𝐿 is good for memory management. Continue the discussion in the next class. Please don't miss the topic of paging. That is very important to understand. Okay. So take care. Good night. Thank you.